Okay, let's discuss this topic because this is important in dealing with wind loads, especially for enclosed and partially enclosed buildings and also partially open buildings. But if in open buildings, there will be no internal pressure. But since this is our lecture today, let's discuss this internal pressure. So I will have an example later, and this internal pressure is based on ASC 7-16. So okay, example, we have like this building, a hangar with open closed door. So this hangar has a door that can open and can close. Then this is the elevation, and as you can see, this is given, okay, and plan. And as you can see here, um, this is what I'm talking about because there are four variables here. AO means it is the area of opening in which that area receives positive pressure, meaning that when the wind blows, it will enter to that opening, that is AO. Then AG is the gross area in which that opening is located. So AG uh, is the, for example here in this example, that is the gross area is 115 times 3, and that is equals to 345. While the AO here, in which if there is a wind that is parallel to the ridge, then this part will receive a positive pressure. If we say that the wind is going inside here, and the opening here is 115. But if the wind is here at the back, then the opening here is 0. So that is AO. So anyway, AG is where we can find AO. Then AOI is the other openings that can be located in the building. For example, here, since in the parallel to the ridge, this is in suction type, in which there is no positive pressure here but negative pressure suction. And let's say example, we have an opening here, a window, then that is AOI. Okay, later we can see that meaning of ano there. Then AGI is where that is the total, no? Total surface area minus the area gross. So this is what I'm saying, no? So additionally, we have internal pressure, and first we must determine the enclosure classification because if it is enclosed, that is plus and minus 0.18. If it is partially enclosed, that is positive 0.55 and negative 0.55. In which partially enclosed buildings has the highest internal pressure among these enclosure classifications, while open buildings, since it is open, there will be no internal pressure. So these are the variables I'm talking about. AO, this is from ASC 7-16, Chapter 26, or you can also find it in NSCP Section 207A. That is in the symbols and definition part of the code. So as you can see here, that is the area of openings in a wall that receives positive external pressure, meaning this is the opening in which wind may enter. So don't forget AO, that is in which the wind may enter and create internal pressure in your building, and this is very important in design loads for wind. So that is why I am discussing this. Then AG, so like I said earlier, that is the gross area. So gross area, not the net area, it's the gross area. So we have earlier I said we have 115 square meters because the opening is 115 square meters, so 345 all in all. So next, AOI is the sum of the total areas in which, including walls and roof, but not including the area opening in which there may be, it is the opening in which the wind may enter, because this is the wall that receives positive external pressure. Then finally, the AGI, like I said earlier, this is the sum of all gross areas, not including AG. So therefore, total gross surface area minus AG, that is AGI. Okay. Um, so let's talk about this for the first scenario in which the wind normal to the ridge. So as you can see here, only the windward wall receives the positive pressure because um, we basically know that roofs are always in suction, although there is some part of it, like for example in the table 27.3-1, there are positive a pressure in wall if the CP is positive. But anyway, mostly walls are, in example, in this case we have a hangar. Roofs are considered as closed. No, there's no opening in walls. No, unless if you have openings in walls. But as you can see, AO means the wall. No, wall only, because that is the definition of ano. But anyway, let's continue. So as you can see here, this is our AO. Since we have no opening, because the opening here is only in the door, in which, as you can see here, this part here, no? As you can see, this is the door. But as you can see, this is a negative pressure, and AO means simply means that is a wall that receives positive pressure. But AO here is in a negative, so uh, we don't have AO, so AO is zero, because here we assume that, for example, uh, we have no, in this part we have no opening, so that is AO. That is based on the case here. AG, so earlier, as you have seen earlier in the previous slides, it is 414, the area of the wall in which we can find that there is no AO, or the positive, or the wall that receives positive pressure. AOI is the other walls or other openings that is not receiving positive wind pressure. Like for example here, this is not receiving positive wind pressure, and it has an opening, the door, 115 square meters. Right, square meters. And AGI is just the total gross surface area minus 414. So So you can see here, AO is 0 and is less than 0.37 square meter, as defined here, no? So you can see as defined in both, because later we can see if it is partially open buildings. But obviously this is not an open building, because open building demands 80% open. So as you have seen earlier, the our plan or our perspective and our elevations, we have no opening mostly. So our opening is the door, only the door for which the airplane will enter. So anyway, this is our 1.1 AOI. This is for checking if this is partially enclosed. So in short, in enclosure classification, we just need to determine if it is enclosed or partially enclosed. And if it's not both, then maybe it's partially open building. So obviously open buildings, you can see it anyway. We are focused on enclosed and partially enclosed. So AOI over AGI is just less than zero point 0.2, and this satisfies, I think, enclosed buildings. Yes. So it satisfies enclosed buildings in a sense that AO is less than 0.37, or whichever is smaller, no? And it also satisfies because AOI over AGI is less than zero point 0.2. So check. So it satisfies check and satisfies check. And let's see if it satisfies partially enclosed. No, it does not satisfy partially enclosed because AO is less than 126.5 square meter. But if it, like for example, it satisfies, then it did not satisfy here, then it can be partially open buildings. But anyway, this is easy to understand, no? You can see here. So let's check if parallel to the ridge. How about the parallel to the ridge? This is for normal to the ridge. So this is scenario A. This is for the normal. No? So let's check if what is the enclosure's classification in parallel to the ridge. What if the wind may enter the door? Let's see. So, as you can see here, class, during strong wind forecast, obviously, if as a designer, you will warn the owner or the user of that hangar to close the door if there is strong wind. So, therefore, if doors are closed here, then we can say that the enclosure classification obviously will be enclosed. So, as you can see here, it's enclosed because the doors are closed. So, this is why, as a civil engineer, it's very important that you inform the owner or inform the user of that hangar that during strong wind, because winds, unlike earthquakes or typhoons, unlike earthquakes, it can be predicted, it can be forecasted, and that is better than earthquake. Earthquakes cannot be forecasted. So if there is a strong wind forecast, obviously you need to close the door, and that is why this will become an enclosed building. So anyway, I'm very sorry. This is not 115. This must be zero. This is zero because there is no other opening. This is zero. I did not change it. So since this is zero and this is zero, oh, AOI 1.1. Okay, it's 115 means there is opening. But anyway, this is for this part, no. This is for this part. If this it's at the back. So 115 is if the is at the back and this is open. So anyway, obviously if doors are closed, it is automatically enclosed. So anyway, that's a simple explanation. That's a logical explanation about that. But what if there is a door failure? So this is some problems with some hangars, no. As you can see here, this is a door failure in a hangar, and I don't know if there is a strong wind here, but there is a failure in the door hanger. If there is a failure in the door hanger, this is what I'm saying. You should really consider another scenario. But for this case, let's try. If there is a door failure, now as you can see, door failures are real. It's not a hypothetical scenario, but it is a very, very much possible scenario that could occur. So this is a real door failure or failure of a hangar door. So you can find this in Denton, Texas, slidinghangardoor.com. Well built doors. No? They try to advertise this one. So this is the enclosure classification. What if there's opening? So if there's opening, obviously our AO becomes 115, and other opening is 0 because the only opening here is 115. And AG is where we can find the opening 115 and AGI. So let's see if this is still enclosed buildings. So there's okay. So it does not satisfy the enclosed. Maybe it will satisfy the partially enclosed. See? You see that if there is door failure and doors are not closed, there is a chance that your enclosure classification of your hangar from being enclosed, it will become partially enclosed. And that is a very important thing to consider. No? So as you can see here, this is our internal pressure. So this is our internal pressure. As you can see, if the doors are closed, both is positive and negative 0.18. So we have no problem in putting load cases if we assume that doors are not does not fail or doors can be closed during high winds, no. And obviously in wind normal to the ridge, since it's still suction type in the area in which the door is open, uh, assuming that doors are not closed in wind dormitories, it's still enclosed. But this is what I'm talking about. This is partially enclosed. No? So as you can see here, if doors fail, the scenario of wind entering your hangar will create greater internal pressure. Oh, so you can see. So that is the difference between the two. So in designing and in considering doors, consider doors that can be closed during high winds or strong winds, because your loading will change. Your loading will change depending on your internal coefficient. So um uh, I think that's it, no? Let's see. Okay, thank you. So, wait for the ETABs on how we can try to input the load cases, because if we consider the door failure, our load cases will become, I think, 12 load cases for winds. And that is, no, I think it's not. Yes, yes, yes. Okay, 4 in wind normal to the ridge with plus minus 18, 4 with winds parallel to ridge plus and minus 18, and another 4 for plus and minus 55 for winds parallel to ridge. But okay, thanks. That's it.